Okay, 42 of them have joined. Okay, that means 26 not joined. Okay, Shital Singh got his official pass ID working. Very good. Right. For a change, it doesn't happen usually. For a change, all the students who are wishing good afternoon, and I hope they are awake. That's why they are wishing. All are boys. This is something different about TY. Anyway, I think I should. अच्छा कुछ गर्ल स्टूडेंट्स का ईगो हर्ट हो गया नाउ दे आर विशिंग गुड आफ्टरनून इट्स ओके इट वाज जस्ट casual observation, nothing serious. Okay, so the last lecture when we ended the last lecture, we were looking at types of scattering. In that, we have seen what is Rayleigh scattering and the factors. We just enlisted factors which will affect the intensity of that Rayleigh scattering. Now, the most we can say most common example is the Rayleigh scattering of blue light in our atmosphere. We discussed this at length in the first lecture for this chapter. So, observe these two glasses. So, scattering by large molecules. Okay, scattering by large molecules with particles of colloidal dimensions, that is significantly large particles. Scattering is sufficiently intense. It is so intense to be even seen by naked eye. What I mean to say is, generally, the fraction of light that is getting scattered when the molecules are small, the particles are small, it is not detected by naked eye because the fraction is very, very less. But as the particle size goes on increasing, that quantity of scattered light goes on increasing. So at colloidal level, even you can observe that with naked eye. Okay, so that is called a Stendhal effect. Again, the scattering effect all again. Now, this is used to determine the size and shape of polymer molecules and colloidal particles. I guess you have done this in physical pharmacy practicals. Have you done or not? I exactly remember, but there is something related to colloidal solutions in physical pharmacy practicals. Did you observe Tyndall effect under microscope? Are you are okay? You are learning totally online from. Oh yes, Anjali. Yes. So in a way it is sad, but yes, it can be done. So that was related to Rayleigh scattering. Now coming to the second type of scattering, the Raman scattering. The Raman scattering effect differs from ordinary scattering in part that scattering radiations suffers quantized frequency changes. In simple term, the light that is scattered has different wavelength than wavelength of the incident light. I repeat, in Raman scattering, wavelength of the scattered light is different than wavelength of incident light. Now, these changes are the result of vibrational energy level transitions that occur in the molecules as a consequence of polarization process. Have you seen ever before changes in vibrational energy level? I will repeat my question. Have you seen before that a molecule is absorbing the energy, and after absorption of the energy, its vibrational energy has changed? Have you seen that before? Yes, Anjali, where you have seen? Okay, Mahipal, you have seen that in IR. Very good, very good. In IR, you have seen. But that effect was observed because of changes in the dipole moment. Okay, so it was dipole moment change related to. Can I say it was related to magnetic properties of dipole? Now, this change is polarizability. Polarizability is electronic effect. So, when molecule interacts with electromagnetic radiation in electrical manner. In IR it was magnetic manner, electromagnetic radiation. अगर magnetic interaction हुआ तो IR है, अगर electrical interaction हुआ तो Raman scattering होता है. So that after that interaction, the molecule temporarily acquires that energy. Okay, and after acquiring the energy, its vibrations will not change. Its polarization will change. The molecule will get more polarized. Are you with me, students? Are you following this? What changes that occur in molecule? Its polarization occurs. Okay, I hope you understood this. Now, let's study more about this type of scattering. Now, basic physical realization. What happens in it with respect to physics? Illuminate a species with laser light wavelength 532 nanometer. After this laser light falls on your specimen, there are two possibilities. Okay, when the light is scattered, not absorbed, just scattered. We are interested in scattered light. Light will be of two forms. I'll first tell you the right hand side, then we will go to the left hand side. So the wavelength of scattered light will be equal to wavelength of the incident light. So it is called as elastic or Rayleigh scattering. Now you can imagine that a rubber band in its resting stage, you provide energy, it get stretched. When you release the energy, it will come back to its original position. So rubber band is elastic. Okay, energy acquired by the rubber band and energy released by the rubber band is same. So wavelength which is released and wavelength which is temporarily absorbed or temporarily acquired, both the wavelengths are same. Now the second type is inelastic or also called as Raman scattering. So the possibility is the material, like consider a metal wire. You are holding the metal wire, you are stretching it. Okay, if that stretching is very small, the metal wire will acquire its original state. But if it is significantly, the stretching is significantly larger, when you release the wire, it will not come back to its original state. It will get stretched. So change will be permanent. So some energy is acquired by the wire. Just a second, students. Extremely sorry for that disturbance. Okay, Mahipal wants me to repeat the first example. See, Mahipal, for time being, forget that this is about any electromagnetic radiation. Just consider that it is about energy. Okay, now you are holding one rubber band in both of your hands. Okay, it is at resting position. You supply the energy and stretch it. So can I say the energy is acquired by the rubber band? Are you with me, Mahipal? Do you agree that potential energy of the rubber band system has now increased? Raman in large molecule वाला
उसके पिछले स्लाइड वाला
आप you are mixing two things. See, this is not Raman scattering. Raman scattering यहाँ से चालू होता है. ये जो हम देख रहे थे, it was Rayleigh scattering only. Okay, this is Rayleigh scattering only. What we are telling is, अभी हमने एक ना बहुत पहले देखा था, एक we tried to correlate with particle size. अगर यहाँ पे देखा रहेगा आपको, बहुत छोटा एटम या मॉलिक्यूल होता है तो क्या, और उसका साइज बड़ा होता जाता है तो क्या, ये हमने यहाँ पे डिस्कस किया था. स्कैटरिंग ऑफ रेडिएशन जब हमने चालू किया था, उसमें हम बाद में डिस्कस करते हैं टाइप्स ऑफ स्कैटरिंग. उसमें हम पहले देखते हैं रेले स्कैटरिंग. रेले स्कैटरिंग में हम देखते हैं स्कैटरिंग ऑफ लाइट. एग्जांपल वाज दैट ब्लू कलर स्कैटर्ड. और बाद में हम देखते हैं कि अगर पार्टिकल मॉलिक्यूल बड़े होते जाता है तो क्या इफेक्ट होता है. तो जैसे वो बड़ा होता जाता है, पहले जब स्मॉल था तो वो जो राइट स्कैटर हो रहा था, इट वाज नॉट डिटेक्टेबल बाय आईज बिकॉज द क्वांटिटी, द प्रोपोर्शन of the scattered light was small. But as the size of the molecule, size of that cluster goes on increasing, the effect, scattering effect becomes more and significant and visible. Did I solve your doubt, Mahipal?
Okay, yes sir.
आपका क्वेश्चन होगा तो पूछो. This is the right time to ask.
सर मैं रमन का बोल रहा था, जो स्कैटरिंग बाय लार्ज मॉलिक्यूल के नीचे लिखा ना, टेंडल इफेक्ट के नीचे, उसका पूछ रहा था रिपीट करने में.
Used to determine size, shape.
नहीं, नीचे लास्ट पैराग्राफ.
तो मैं यही बता रहा था ना. I was going to explain both of them. I will tell again. Let us see. Raman scattering effect differ from ordinary scattering in a part of the scattered radiation suffers quantized frequency changes. I'm coming to this. I'm explaining it. Okay. So where was I? I was giving example of a wire. Okay. I was giving example of wire. So that wire, when you stretch, it remains stretched. It will not come back to its original state. Now, what has happened in second example is, when the wire was released, small amount of energy may have escaped the wire, but majority of the energy remained with the wire. So this is not elastic. The change was permanent. The energy was acquired by the system permanently. Now, suppose this is the ground state. Okay. After acquiring the energy, molecule is going to higher energy state. And when it is falling back, it is not falling back to the original level. It is falling back a little higher than the original level. So there is gain in the energy level, and the photon released from here will be of lesser energy, longer wavelength. Okay. Now this differences the energy acquired by the molecule will depend on different energy levels within the molecule. More specifically, different vibrational levels within the molecule. I hope you remember those diagrams, that there were different vibrational levels, then different electronics levels. Okay. And to the vibrational level, for every vibrational level, there was different rotational level attached with it. Now, in Raman scattering, when energy is acquired, uh, and energy is released. So from one energy level, molecule goes to another energy level. Now this energy difference is fixed. This energy difference is fixed. It is quantized. It is quantized. Why it is quantized? Because in a molecule there will be fixed energy levels. Okay, the energy level will be fixed. There will not be energy transitions which are corresponding to energies in between. Like this transition will not be possible where the molecule has to come here, because there may not be this energy level existing in the molecule. Okay, so there are fixed energy levels for a molecule. The transition from down to up or from up to down will be corresponding to these energy levels only. Energy levels in between, like I will change the color so you may understand better. Okay, energy transitions corresponding to these green lines, which are not part of the molecular level, energy levels, will not occur, never occur. Are you following it, Mahipal, now?
Yes, sir.
Okay, very good. Now, these changes are the result of vibrational energy level transitions that occur in the molecules as a consequence of the polarization process. Now, if you will observe over here, okay, what is incident is unpolarized light. Okay, you understand, I hope, the unpolarized light. Okay, this example now we will come back. You will understand it better when we will see the energy changes. Then we will come back here. So I was giving example of that wire. So it is inelastic because the permanent change was brought into the wire. Its energy changed, its shape changed permanently. So in this, in case of inelastic, light experiences Raman shift in the wavelength. Okay. So whatever change is there, lambda incident minus lambda scatter is Raman shift. I'm sorry, it must be feeling that someone has sneezed into your ears. So it is like, see, there are N2 molecules. This is one atom of nitrogen. This is another atom of nitrogen. And this is the bond between two nitrogen represented by the spring. Okay. So this is the laser light falling on it. So when laser light interacts with the bond and makes the nitrogen molecule polar momentarily, it causes Raman scattering. Now, please understand that for infrared radiation, nitrogen molecule was transparent. It did not absorb any IR light, but this is not true for Raman scattering. In fact, nitrogen is the main, can say, a very major source of scattering. Okay, the Raman intensity is about 0.1 ppm of the incoming laser intensity. So, inelastic light scattering mechanism. Let us see how that Raman scattering occurs. Now, Raman shift can be, there are two types of Raman shift possible. To lower wavelengths, it is called as Stokes scattering, and in this, the energy is lost and predominant Raman shift is observed. Now, when we'll see the mechanism, you will understand it better. Okay. Now, there is second type where the Raman shift is to the shorter wavelength it is called as anti-Stokes scattering. Energy is gained and it is called as subordinate Raman shift. Okay, you will understand this better. See, this is the initial energy level. This is initial energy level. The laser light is bombarded on the molecule. After bombardment of that electromagnetic radiation, the molecule is absorbing one photon and it is jumping into this energy level. But when it scattered that light, I should not say the electromagnetic radiation was absorbed by the molecule, I should say it was momentarily retained by the molecule. When the energy was released, this was the final energy level of the molecule. Now, final energy level is higher than initial energy level. Okay, that means energy is gained by the molecule, but the electromagnetic radiation has lost the energy. Electromagnetic radiation has lost the energy because when the energy was released, it was something less than the original. So you will get longer wavelength. Have you understood this first part, students? Have you understood this first part? Energy gained by the molecule, energy lost by the electromagnetic radiation. So the second will be exactly opposite. Subordinate Raman shift will be exactly opposite. See, this was the initial level. Energy acquired by a molecule. When it released, the energy release was more than that of the photon that was incident. So it is anti-Stokes scattering. Now the molecule has actually lost the energy and electromagnetic radiation has gained the energy. So it will release shorter wavelength. Shorter wavelength have more energy. So it is releasing shorter wavelength. That's why this effect is called as subordinate Raman shift. Observe this diagram. If you have any doubt, do ask. Okay, so let us see the photon interpretation of this. Now, a Raman effect is a two photon scattering process. Okay, that is one photon that is incident, the other photon that is scattered. So two photons are involved. These processes are inelastic scattering. So first, let us see what is Stokes scattering. What we have seen in previous slide, there is different representation of the same thing. Energy lost by photon. How energy will be lost? See, this is your molecule, and you can see that this is photon in. Okay, the molecule originally was not vibrating, but when proton left the molecule after scattering, the molecule is now vibrating. वो कार्टून में दिखाते हैं ना, ऐसा bucket जैसा structure दिखाते हैं. So it is like the person or the thing is vibrating. So this is vibrating there. Okay. So how about anti-Stokes scattering? Energy gained by photon. So the molecule was originally at higher energy level, it was vibrating, and at that point it momentarily absorbed photon in. And when proton left, scattering the vibrating, the molecule has now stopped vibrating, and the photon released has now gained the energy. What if the scattering is Rayleigh scattering? The molecule, photon in, it is no vibrating. Photon out, it is still not vibrating. So energy of the incident photon and the photon that left the molecule is same. In incident photon, energy E, vibrational energy EV, then in terms of energy, photon out has energy equal to E minus EV. Okay. Now, for this first term, I will explain E again. E is incident photon energy. And what is EV? EV is vibration energy, and what we are looking at here is energy of photon out. Let us consider that EO, photon out. Okay, this is the statement for Stokes. This is statement for anti-Stokes scattering, and this is statement for Rayleigh scattering. Do you agree with these statements, students? Go through, try to understand. If you don't understand anything, do ask me. And if you have understood, please type down that we can proceed. Chaitanya, what you want me to repeat? The last three equations are you talking about? Are you talking about those equations? Okay, she said yes. Okay. So energy of photon which is leaving the molecule, like let us say photon out energy in case of Stokes scattering is equal to incident photon ka energy minus vibrational energy. Now this vibration energy किसका होगा? molecule का. Okay, so whatever difference in them is equal to photon out का energy. Now, what has happened in Stokes scattering is, see, in the Stokes scattering, photon has lost some energy to vibration and it has got now less energy. Original energy was more and this energy is less. That's why this is a smaller number, this is a larger number. So if this is larger number, where the energy has gone? It has gone in the process of, in the motion of vibration. Now, in case of anti-Stokes scattering, this is the energy of the proton that is released. This is the energy of incident photon. Now, incident photon has got less energy than that of the outgoing photon. So it has gained the energy. From where it has gained the energy? It has gained the energy of vibrations of the molecule. So it is EV. In case of Rayleigh scattering, the incident energy and the scattered energy, both of them are same. Chaitanya, do you understand now? Okay. Any other doubts? Anybody? Okay, this is another representation of the same thing. I will keep this slide for 30 seconds. Just go through it. Try to understand. Okay, let us see the another representation of what we have observed. So keep in mind that Stokes scattering, anti-Stokes scattering, and Rayleigh scattering, everything happens simultaneously within molecule. It is not that in a set of, say, in a set of 100 molecules, all 100 will give either Rayleigh scattering or it will give you Raman scattering. No, it will not happen. All the molecules will give you all sorts of scattering. Now, as I am reading, you observe this diagram. Okay, a Raman spectrum can be done by irradiating sample of carbon tetrachloride with an intense beam of argon laser having wavelength of 488 nanometers or 20,492 centimeter inverse. The emitted radiation is of three types: Stokes, anti-Stokes, and Rayleigh. You can see Rayleigh scattering over here, which has got maximum intensity. ये तो छप्पर फाड़ के ऊपर जा रहा है, इसका पीक कहीं पे, अरे उसका जो पीक है हमको वो कहीं पे तो इधर पे मिलेगा ऐसे. ओके, तो छप्पर फाड़ के ऊपर जा रहा है वो डायग्राम का. ओके, the most intense scatterings are Stokes scattering after Rayleigh scattering, and then you get anti-Stokes scattering. Remember why we get Stokes scattering and why we get anti-Stokes scattering. In Stokes scattering, energy is gained by the molecule. In anti-Stokes, energy is lost by the molecule. In Stokes scattering, energy is lost by electromagnetic radiation. In anti-Stokes scattering, energy is gained by electromagnetic radiation. Because energy is gained by electromagnetic radiation, you will get anti-Stokes over here, and in case of Stokes, because energy is lost, you will get their peaks over here. अच्छा, we are getting it because it is in wave number. अगर वेवलेंथ में होता था तो ये एग्जैक्टली उल्टा होता था. आई होप आई एम नॉट कंफ्यूजिंग यू. अच्छा, अगर कंफ्यूजन हो रहा है तो ऐसे याद रखो कि हमको रमन स्पेक्ट्रा मिलेगा, उसके एक्सिस पे सेंटीमीटर इनवर्स होगा, वेव नंबर होगा. तो अगर एनर्जी बढ़ता है इलेक्ट्रोमैग्नेटिक रेडिएशन का तो एंटी स्टोक्स मिलेगा, एनर्जी कम होता है तो स्टोक्स मिलेगा. अच्छा, लुकिंग एट द डायग्राम, which effect is prominent, which scattering is prominent out of these three? सबसे ज्यादा कौन सा scattering मिलता है? अच्छा, I will simplify my question. Out of these three types of scattering, for which type of scattering you are getting the highest, most intense peak? Very good. तो for Rayleigh, उसके बाद किसका नंबर आता है? Stokes. Very good. And सबसे weak कौन से peak होते हैं? Anti-Stokes. Brilliant, brilliant, very good. So if you want to study Raman spectra, which peaks you will be most interested in? Let us see who can answer it right. क्या बात है, रोहित एंड महिपाल पहले बॉल पे चौका मार दिया. वेरी गुड. साक्षी, वेरी गुड, एक्सलेंट. सो वी आर इंटरेस्टेड इन स्टोक्स टाइप ऑफ स्कैटरिंग, क्योंकि रेले में जो स्कैटरिंग हो रहा है उसका कोई मतलब ही नहीं है. whichever wavelength is incident on the substance, the same wavelength is getting scattered. तो रेले आपका कुछ काम का ही नहीं है. तो काम के कौन सा है, स्टोक्स और एंटी स्टोक्स. लेकिन एंटी स्टोक्स का इंटेंसिटी इतना कम है कि उसको कौन डिटेक्ट करेगा. तो एंटी स्टोक्स भी काम का नहीं है. वी विल बी यूजिंग मोस्टली स्टोक्स. ओके, so again this is another representation of energies. Go through it, we have discussed this. Instead of just telling energy, we are telling that energy as a function of wave number, frequency. So E is equal to h nu. This relationship is used here. अगर कुछ समझ में नहीं आता है ये स्लाइड में तो पूछो. Okay, let's go forward. Excitation of Raman spectra. The abscissa, that is x-axis of Raman spectra, is wave number shift delta nu. It should be delta nu bar. Student, it should be delta nu bar. Make that correction. If you are taking notes, it should be delta nu bar. Nu bar means wave number. When we say nu, it is frequency. Nu bar is wave number. Okay. Anyway, coming back. So, original wavelength minus scattered wavelength, if it is equal, it will become 0. Then you will get a Rayleigh scattering. Okay. If original wavelength is less than the, if the scattered wavelength is shorter, then you will get anti-Stokes. If scattered wavelength is longer, you will get Stokes. Okay, so I will repeat the first point. The abscissa of Raman spectrum is number of shift, is the wave number shift delta nu 0, which is defined as the difference between wave numbers between the observed radiation and that of the source. So for CCl4, 3 peaks are found on both sides of Rayleigh peak. Rayleigh peak you can consider as the origin. There are 3 peaks on left hand side, 3 peaks on right hand side, and that pattern of shift of each side is identical. See, this is minus 218, this is plus 218, this is minus 314, this is plus 314, this is minus 459, this is plus 459. So both sides are identical. Anti-Stokes lines are appreciably less intense than corresponding Stokes line. For this reason, only Stokes part of the spectrum is generally used. The magnitude of Raman shifts are independent of wavelength of excitation. See, whichever wavelength you select, it doesn't matter. If you are selecting 532 nanometer, it is okay. If you select wavelength as 300 nanometer, it is still okay. You are still getting the same spectra. Why? Because on y-axis, you are calculating the difference in the wave number. You are not, this is always be relative. Okay. So if you are starting with say 500 here, 532, 532 minus 218, you will get this. 500 plus 218, you will get this. Okay. So another representation of the same thing. Now let us compare Raman spectra with IR spectra. For a given bond, the energy shifts observed in a Raman experiment should be identical to the energies of its infrared absorption band, provided that the vibrational modes involved are active towards both infrared absorption and Raman scattering. Now for Raman scattering, almost all the bonds are, but it is not necessary that it is active for infrared radiation, like for those homoatomic molecules. Now coming to the second point, the differences between Raman spectrum and an infrared spectrum are not surprising. Infrared absorption requires that vibrational mode of the molecule have a change in dipole moment or charge distribution associated with it. So this we have seen in first lecture only. In contrast, scattering involves momentarily distortion in the electron distribution around a bond in a molecule, followed by remission of radiation as the bond returns to its normal state. So there is no change in vibrations. It is only momentarily polarization. In its distorted form, the molecule is temporarily polarized. That is, it develops momentarily an induced dipole. that disappears on relaxation and remission. The Raman activity is given vibrational mode by differ markedly from its infrared activity. Now, what are the factors that affect polarizability? First is atomic number Z. So, polarizability is directly proportional to the amount of electrons present. So, as the atomic number goes on increasing, amount of electrons present within the atom will go on increasing. So, the outer electrons which are away from the nucleus will be less and less controlled by the nucleus. So as the atom size goes on increasing, the number of these loose control electrons goes on increasing. So molecule in which that atom is present becomes more polarizable. Then second comes bond length. This polarizability is directly proportional to bond length. So more the bond length, more is polarizability. When will be the bond length larger? When the atom is large or participating functional groups are large. P is again directly proportional to the size. See, size of molecule here we are talking about. So molecular orientation with respect to electric field, parallel or anti-parallel. So that will also affect it. Then bond strength. It is also called as bond order. So whether there is double bond, triple bond present. So it is inversely proportional to the strength of the bond. What it means is, if there are double and triple bond present, it will be difficult to polarize those molecules. So because they are strong bond, so bond length will get shorter and it will be very difficult to polarize these bonds. Then electronegativity difference. If there is lot of electronegativity difference, the bond length will be shorter, the atoms will be very close to each other, and it will be difficult to polarize such bond. Then last one, covalent bonds are polarizable than ionic bonds. Now, immediately what comes in mind is, sir, ionic bond is already polar bond. So something which is already polar, it is difficult to make that bond more polar. A covalent bond, comparatively less polar, will be in a way easy to polarize it. Now, instrumentation, we will study that in next lecture. So start giving your attendance. Let's start with roll number 1. Let us start with roll number 1. Hurry up, students. 1, 2, 3, 4. Hurry up, hurry up. Okay, thank you, Chaitanya. Thank you, everyone. You may disconnect. And please do check Google Classroom. I uploaded most of the things now. If you need anything else, you may ask me. You may disconnect. Okay, cost of 53 present. Got it.